Okay, linear regression. Sometimes referred to as the line of best fit. It's the layman's term. We use this technique when I have data that appears to be reasonably linear, and I'd like to make a model for that data. And there's a big difference between being reasonably linear and actually linear. If I have a set of points that are perfectly linear, then I would expect, if I drew a straight line, imagine that's a straight line. That's not exactly perfect, but every single point would have to be exactly on the line. So this is what a linear relationship is. Also, if I calculated the average rate of change between any of those points, I would always get the exact same amount each and every time. Well, the problem is, in the real world, not everything is perfectly linear, but a lot of times it's close enough. For instance, I might be looking at some data that looks like this. Clearly, these set of points are not linear. However, they're reasonably close to being linear. Because they're reasonably close to being linear, I can model it. And a very important concept about modeling. That means I'm making, in essence, a replica, not the exact item. So when I model it with a line, I'm making the closest I can come to the data with a straight line. So where should we place the line? And it's very, very important. The idea is the line should be as close to all of the points as possible. In essence, I can view this data as a highway. Here's my highway of the data. And all of the data are on this highway. If I'd like to make a model that best explains the data, I'd like the line that goes straight through the center. So this would be my best fit line. And that is, in essence, what I'm trying to find. Now, very important, a lot of people want to get lazy with it, and you can't get lazy with it. Students will ask which points to use. All of them. None of them is the correct answer. I'm not using this point and I'm not using that point. I'm using them as a collective group. I'm not trying to describe the first and last point. I'm not describing the second and first point. I'm describing all of them. And because they're not linear, I'm not trying to go through any two of them. I'm trying to go through all of them. It's a very important concept. Let me explain in more detail. I'm just going to put up a couple of points. Let's wanted to make a line of best fit through these 5 points. I don't want to connect the first two and say that's the best fit line I can come up with. That clearly does not best model all of the points. That might be the best model for the first 2 points, but that clearly does not describe all of my data the best way that I can. If I tried just to connect the first and last point, sure, I can come up with a line just by connecting the first and last point. But again, Now looking at this point and this point, they're not really even close. So connecting the first point and last point is not an effective way to model all of the points. Really what I have to do is look at all of the points as a collective group, look at the overall pattern that all of the points are making, and then try to go through the center collectively. Maybe not the best. Let's see, but fairly close. I might want this a little higher on the end. That's a little bit better there. And what I'm looking at is how far is the distance between my line and my points. And I want the line that comes the closest to all. Not to the first, not to the last, not to the second, not to the ones in the middle, but looking at every single point, I want to minimize the distance between my line and my points. Now, luckily, we have a calculator technique that allows us to do it. Trying to find exactly where that line is to minimize the distance is very difficult to do the arithmetic on it. It's huge. So we're going to introduce a calculator technique.